Welcome everybody for this Friday's ICS seminar. We have the great pleasure to have Sean Raymond with us today to give a seminar about the bombardment on distant worlds. And I will simply make a short introduction of the career path of Sean Raymond. So he is originally American or half American, half Irish. He did his PhD at the University of Colorado, where he also did a NASA postdoctoral fellowship later on. Then he was a visiting scientist at the observatory in Bordeaux in France, where he's actually now working. After this, he went back to the University of Colorado as a research scientist. And since 2009, he is a CNS researcher at the observatory in Bordeaux, France. And Sean Raymond has also, he has written a book, or he's actually not only a researcher, but also a poetist. Now, how do you say?
Just a poet.
A poet, yes, exactly, a poet. So you can also buy a book from Sean Raymond. It's a collection of diverse poems called Black Holes, Stars, Earth, and Mars. And yeah, you can even buy it on Amazon. So Christmas time is approaching. So maybe this is a perfect gift for families. So, but now we come to the science part of Sean Raymond's work. And Sean, the floor is yours. The screen is yours. Yes.
Well, thank you so much for the introduction, and thanks for encouraging people to buy my book. But so I'll talk science today about a new project about bombardment of distant worlds. Right. So the real title is An Upper Limit on Late Accretion and Water Delivery in Trappist-1, but it sounds cooler to say bombardment of distant worlds. And you guys are lucky or unlucky in that this is the first time I'm giving a talk on this subject. So it'll be interesting to see how it goes. So here we go. So the idea here is to present this kind of new study. I'm Sean Raymond, as Caroline said, and I want to acknowledge all the collaborators on this project who are listed down below. It's actually a very Swiss project. There's 4 of the 11 authors on this paper are based in Switzerland. Emeline Beaumont is in Geneva, and so is Martin Turbet, or he was when this happened, and Caroline Dorn in Zurich, and Simone Grimm in Bern. So well done, Switzerland. All right, moving on. So the subject of my talk is bombardment or late accretion, basically impacts on planets after they form. And so what I'll talk about is a little bit about what we know on Earth, how we know it, and what we think, how that affects how we think Earth formed. And then we'll switch and look at exoplanet systems. And we'll focus on the Trappist-1 system, talk about how we can learn stuff about what may have bombarded or accreted onto those planets after they formed, and how that ties in with formation models of systems in general, and where they get their water. So here we go. So if we're talking about bombardment or late impacts, after planets mainly formed, why should we care about such things? So this is just to motivate the interest in late accretion. So late impacts can do things like deliver volatiles, such as water, to a planet. That's always something of interest. They can either create, erode, or modify atmospheres, either by delivering atmophile elements, or by impact erosion of an atmosphere that's already there, or just by changing the composition of the atmosphere. They can also cause extinctions, of course. There's a million photos on Google of dinosaurs getting wiped out by impacts like this, and it's always T-Rexes. I always feel bad for them because they're the ones chosen for these images to be the face of the asteroids killing off dinosaurs. And finally, impacts also set the stage for ridiculous movies. There's so many movies about asteroids bashing into Earth. My personal favorite is Deep Impact, but there's lots to choose from. So now that we know why we care about planets' impacts, how can we measure a planet's impact history? So the best way is just see impacts happen. If you have a camera, watching a planet for a billion years, you can see all the impacts that happen. And of course, it's not practical, but once in a while we get lucky and we do see this. For example, the best known case of this is comet Shoemaker-Levy 9, which first passed close to Jupiter and was torn into a bunch of fragments. And then a couple years later, those fragments crashed into Jupiter, and we have direct images of the aftermath of those impacts, like this one with the Hubble Space Telescope. Of course, you have to be insanely lucky to have this happen, but it does happen. A more practical way to measure the impacts on a planet's surface are with craters. Since each crater is thought to be from a specific impact, counting the number of craters of different sizes can tell you something about, how much stuff is bashed into a planet's surface. And a kind of key concept here that we'll come back to is time zero. So if you're looking at craters, time zero is the last time a given surface was resurfaced, was kind of covered up. And then you can measure impacts starting from there. Okay. And so the concept of time zero with different measurement techniques is going to come back again and again. And if in the best case scenario, such as on the moon, when there's both really good measurements of a number of craters, and also we have some rocks that can that can be aged with different isotopes, different radiometric techniques, so that we have ages of certain rocks and that are associated with given craters, what we can hope to do is to determine the impactor flux on that surface as a function of time. And so this plot is just showing different models for the impactor flux on the moon during its very, right after it formed at 4.56 billion years. And so this is the source of controversy related to, for example, the terminal lunar cataclysm, this late heavy bombardment idea, which is kind of going away now. But this type of analysis is behind that. I'm not going to talk more about the case of the solar system in terms of bombardment, but that's where it comes from. Now, for the Earth, this doesn't work too well because we don't have enough craters, and we don't have a lot of craters on Earth. There's only about 200 that are known. And the reason for that is simply that geology covers them up. And so tectonics buries them and biology covers them up. And so we can't do this very well for Earth. So what do we do instead? The best technique we have right now for measuring kind of the accumulated impacts on Earth is using highly siderophile elements. And so these are things like rhenium and osmium and iridium and platinum and gold and stuff. Right? And so I'm not a geochemist, but I can give you kind of the simplified version of how this works. The term highly siderophile element, siderophile means iron loving. And so these are types of elements that very strongly like to go to the core of planets. So they're very strongly segregated into the core. And so you can imagine if our Earth formed by accumulating a bunch of rocky and iron-rich stuff, and then the core formed, all of those highly siderophile elements should have gone into the core, right? Yet we have gold in our jewelry and stuff. So why is that? Where did that come from? And so to answer that question in a very simple way, I'll go to a cartoon version of the late phases of Earth's growth. So again, here we are in cartoon land in a disk of stuff around the young sun. And we're going to kind of just look at a very simple way of how Earth's late accretion may have happened. So first of all, what are we looking at? We're looking at kind of the final assembly where there's a population of, say, Mars-sized planetary embryos and a bunch of leftover planetesimals. And these are the actors that are going to bash into each other and grow the Earth. And just in this cartoon version, the gray stuff is rocks and the red stuff is iron or highly siderophile elements. And you can see the way I've drawn it, the planetary embryos are differentiated. So all the iron stuff is in the middle and the rocky stuff is outside, and the planetesimals aren't. Maybe some planetesimals were differentiated. Also, it doesn't really change the story. So let's call this one the proto-Earth. And you can imagine, right, at this snapshot, there's no highly siderophile elements in the mantle. It's purely rocky or lithophile. Then some planetesimals bash into it, and then boom, you got some highly siderophile elements in the mantle. But then there's an impact between two planetary embryos, and that has so much energy that it causes a new core formation event, and all the highly siderophile elements go to the core. And so then there's no more highly siderophile elements in the mantle. And so you can kind of see where this is going. It's a pretty simple idea. Let's jump forward in time a little bit. The proto-Earth is now pretty big. it grabs onto some planetesimals, then it has a big impact. The last giant impact on the Earth is thought to have been the one that formed the moon. And that probably had enough energy to sequester all the highly siderophile elements into the core. And then, the final impacts of planetesimals after that, after the moon forming a collision, are where we have, that's the reason we have highly siderophile elements in the mantle and the crust now. Right? And so going back to the concept of the time zero for this method is the moon forming impact. That's when we think most or all of the highly siderophile elements were sequestered into the core. And so anything we have in the outer parts of the Earth came after that. Okay? And so by balancing the abundance of highly siderophile elements that are measured and comparing it to some kind of possible source population, like chondritic meteorites, you can make an estimate of about how much stuff we think bashed into the Earth after the moon forming impact. And studies indicate that was probably something like 0.5% of Earth's mass. So after the moon forming impact, only a little bit of late stuff. Late accretion was only about 0.5% of Earth's mass after that point. And that's sometimes also called the late veneer as well. There's a couple other interesting things that we know, or we think we know about late accretion that are kind of interesting before I jump to exoplanets. So one is that the timing of the moon forming impact actually connects with the amount of late accretion. And so from the cartoon you saw before, there's planetesimals and planetary embryos bashing into each other to form planets. And you can imagine if the last big impact on Earth happened early, then there would have been a lot of planetesimals left over to bash into Earth late. And if the last big impact was very late, then the amount of planetesimals left over would be less. And so you naturally expect kind of a trend where the later, a later final giant impact on Earth should have less late accretion. And in this plot, that's what you see. What this plot is showing is the relative amount of late accreted mass on a planet as a function of when the last giant impact happened. And so each of these dots is an Earth analog from a simulation of the formation of the terrestrial planets. And so you can see, as you would expect, when the last giant impact happens early, you get a lot of late accretion. When it happens late, you don't get much. And what's interesting is that the numbers, you can put numbers on this, and it works pretty well. So this horizontal band here is the actual, roughly measured amount of late accretion on Earth, about 0.5% of Earth's mass. And by matching it to where the points fall, where the simulations fall, you can roughly derive the timing of the moon forming impact. And it suggests that it happened something like 100 million years after the start of planet formation, which is actually in really good agreement with other techniques for dating the moon forming impact, such as hafnium tungsten isotopes and things like that. So that's kind of neat. Another interesting thing that we know that connects directly to the story we're gonna tell later is that we think Earth's late accretion was dry. So why do we think this? So this plot is showing two isotopes of molybdenum, and it's basically showing a bunch of different types of meteorites and then some interesting rocks. So let me go through it a little bit at a time. So the blue dots are all carbonaceous meteorites. Okay. And so, and the red ones are called non-carbonaceous meteorites, and they each follow their own patterns, and those patterns are separate, right? And this is a really big thing in meteoritics over the past 10 years or so, showing that instead of 18 different classes of meteorites, there's really only two fundamental ones, the carbonaceous and non-carbonaceous ones, and those are the blue and red lines. Okay? And so we think that the carbonaceous meteorites they came from bodies that started off beyond Jupiter and Saturn's orbits. They're the likely source of water on Earth. And so they're a class that started in a whole separate outer part of the solar system, whereas the red ones we think are the ones that formed, the non-carbonaceous ones we think are more representative of most of the stuff that grew the rocky planets. And so the red ones, the non-carbonaceous, follow this curve. Earth is a little bit off of the red curve, indicating that it probably got a little bit of material from a carbonaceous source, and that's probably what brought the water to Earth. Now, these yellow dots are lunar impactites. They're rocks they were actually brought back by the Apollo missions that we think sample the stuff that was bashing into the moon, the late impactors onto the moon after it formed, of course. And the punchline here is that they follow the red dots. Right? So what does that mean? That means that they are representative of the inner solar system stuff, which we think was dry. Right? And so that's the punchline here, is we think that the stuff that was doing the late accretion was dry. And this is a brand new result, and it fits well. There's some other studies that show the same thing, that we think late accretion was dry. And so what does that mean? It means that if late accretion was dry, then Earth's water must have been delivered earlier. And so water on Earth had to come before late accretion started. And this late accreted stuff is probably just leftovers from the rocky planet's actual formation. So just to recap this part on late accretion on Earth before we get to exoplanets, about 0.5% of Earth's mass bashed into the Earth in planetesimals. Time zero for that was the moon forming impact, something like 100 million years after the start of planet formation. And we think it was pretty dry. And so, like I said, meaning that Earth's water had to have been incorporated during its formation, not during late accretion. So now let's jump to exoplanets. So we'd love to possibly constrain late accretion on exoplanets. And let's go nuts. Let's not say on any exoplanets, but on rocky exoplanets. Right? So how could we try to do such a thing? Well, here's the demographics of exoplanets. It's a slightly out of date, a few years old now, but the general populations haven't changed. You can see a few distinct clumps here. Right? There's the hot Jupiters close into their stars. There's kind of more normal Jupiters further out. And there's this giant clump of hot super Earths and mini Neptunes and stuff that are down around, 100th of a Jupiter mass or so. And I put the actual, planets that fit onto the graph in the solar system here as well. So you can see these planets down at the bottom part of the super Earths are roughly Earth mass or so, we think. And if you zoom in on there and look at the occurrence rate of different types, different size of planets, then there's kind of an interesting distribution. This was found a few years ago by Fulton et al. And what they show is for small planets, right, planets between the range of less than say 4 or 5 Earth radii, there's this cool gap, right? There's this gap where it looks like there's 2 populations of planets that sort of overlap. And there's been a lot of work on interpreting what this means, and the current thinking is summarized as follows: that basically the smaller planets are probably rocky, and their sizes really represent their actual surfaces, whereas the larger ones that are 2 or 3 Earth radii are more likely gas-rich, kind of scaled-down versions of the ice giants, like sub-Neptunes they're often called. And so I mentioned this just to say, if we're going to shoot for constraining late accretion on a given rocky planet, well, then it'd be nice to have ones that are, about the size of the Earth. We don't want ones that are 2 or 3 Earth radii. Those would be interesting also, but they'd be harder to compare with Earth. Of course, how are we going to do this for exoplanets? There's no craters. We're not going to see craters for a long time. We're not going to be able to measure any highly siderophile elements. We're never going to see impacts in real time unless, again, we're super lucky. Some people have tried to constrain impacts using dust production, which is possible, but it's very tricky, and there's lots of interpretation, what makes sense. So it's not too optimistic. So what I'm going to show you is that there is a way to do this. Unfortunately, we can't go and ever say exactly this amount of stuff bashed into this planet, but we can put constraints on this. And so the key idea comes from admitting that we're never going to have the exact number, but instead saying, is there any way to say that there cannot have been more than a certain amount? And I've got a picture of a baby here for a reason. Right? I'm not just randomly showing a picture of a baby. Many of you know, hopefully, maybe all of you know, that babies are messy eaters. Right? And so we're using babies as a metaphor here, of course, for planets. So babies are messy eaters. So when babies eat, it looks something like this, right? They get covered in splotches of stuff. Right. So if you come into someone's house and there's a baby sitting there at the table covered in goop, yeah, maybe they were eating and they got goop everywhere. Right. And then you can flip things around, do the reverse. If you come and you see a baby that's clean, that means that baby did not eat. Yeah? And so if you imagine that the baby eating and throwing stuff all over the place is kind of like, impacts onto a planet. The cleaner it is, then the less stuff could it impact. And so the definition of clean here will be important. So what I'm going to argue is that you can think of a certain subclass of planetary systems, those with multiple resonances, or resonant chains as they're called, as clean babies. And so we know of a handful of these systems that are well characterized now. The GJ 876 system was the first one that was known, and now there's 5 or more known with at least 4 planets in a chain of resonances. What's the kind of general argument is this: we think that these resonant chains are fragile, right? They're dynamically fragile. They shouldn't easily resist perturbations, right? So the fact that we see them means that these resonant chains have not been perturbed very much. And the question is, well, what does that mean, very much and fragile? What are we actually talking about? Can we actually say anything interesting using these terms? And I'm going to argue that yeah, we can. So we're going to focus here on one case, kind of one of the most iconic exoplanet systems that we know of, the Trappist-1 system, that has 7 planets that are each, within 20 or 30% in size of the Earth. And, they orbit a very small ultra-cool dwarf star. Here's the statistics of the planet here. The central star is an ultra-cool dwarf, about 9% the mass of the sun. Its size is about 12% the size of the sun. Its luminosity is very, very low, such that even though the planets are very close in, they receive insolations that are similar to the terrestrial planets in the solar system. The age of the system is debated. It's possible that it's 8 or so billion years old, but it's also possible that it's much younger. There's 7 planets. They're each between about 0.75 and 1.15 Earth radii. And all 7 planets participate in this resonant chain. And I've labeled the resonances down below. The inner 2 ones are a little bit weird, 8 to 5 and 5 to 3. The outer ones are more standard, 3 to 2 and 4 to 3 resonances. And thanks to their being close to resonance, actually, transit timing variations have been able to nail down the masses of the planets to within about 5% accuracy, which is really impressive. And so thanks to that, we wanted small planets because we were hoping that they would be rocky, like Earth. And now we know that these planets really are rocky or so. And so this plot is showing this planet, radius versus mass. And you can see the solar system's terrestrial planets are the small dots here for Mars, Venus, and Earth. And the arrow ellipses here are shown for the 7 planets of the Trappist-1 system. And we'll talk about this more in a little while. But you can see they fall very close to Earth-like composition. The details will matter in a moment, but they look roughly rocky at this point. Yeah. So let's talk more about resonance. So resonances are really just repeated orbital alignments. And here's a nice animation of the Trappist-1 planets as they move along. So let's focus on the outer 3 planets. What you can see is, just in simple terms, anytime the 3 planets are in a conjunction, so they all fall in the same line, they're never all 3 on the same side of the star. And what's good about that is that means it's kind of a stabilizing effect. If they're all on the same side of the star and they're all closer to each other, it tends to have a cumulative gravitational perturbation that can destabilize the resonance. So those kind of resonances do happen, but they don't generally survive, so we don't see them for too long. So this is just kind of, a very cartoony version of what the resonance looks like. In practice, the way we quantify the resonance is using different angles. And so these angles measure kind of the relative positions of the planets at conjunction. And so we use different kinds of angles, things like these resonant angles, these theta values, and also Laplace angles for 3 planets. And so what this plot is showing is that different angles within the Trappist-1 system are confined to a range of values, a narrow range of values. So for example, this top plot is showing the 3 to 2 resonant angle between planets D and E. And you can see it's kind of clustered around 180 degrees. And this kind of clustering around a given value is called libration, where it's bouncing around a certain value, not going everywhere. If the angle is going everywhere, that's called circulation, and it's not in resonance anymore. Okay? And so you can see this is happening for all these different angles. Down below are angles that are related to 3 planets at once. So not just 2 neighboring planets, but 3 neighboring planets. And so in particular, the bottom one, this angle phi 5, is one that we will use a lot to constrain whether the outer 3 planets really are in a resonance. And the goal here, what we're going to do is a very simple numerical experiment. Okay. So the idea is we'll start with the Trappist-1 system using a best fit solution that we have from transit timing variation analysis, including lots of other data. And then we'll assume, we'll say, well, what if there was some leftover stuff after the planets formed? And this is kind of analogous to late accretion on Earth. Like we said, late accretion on Earth, we think came from leftover junk that was floating around after the planets were formed. Maybe that happened in Trappist-1. If that did, well, what would this late accretion, what would this leftover stuff look like? And we tried 2 kind of extreme cases. One being that there was just one leftover rogue planet, as I call it, or a swarm of smaller things. And I tried different numbers of smaller things, trying to optimize where I get the right, the same answer without having too many particles. And we tried about 1,000 rogue planetesimals. That seems to work pretty well. Okay. And so the experiment really comes down to a very simple thing of saying, well, what's the minimal perturbation from these rogue objects that will destroy the resonances? Or, flip on the other side, what's the maximum perturbation that could have taken place without destroying the resonant chains that we see? And the way we address this is using n-body simulations that ran for about 10 million years or so. And that doesn't sound super impressive, but I had to use a tiny, tiny time step to accurately resolve everything. And finally, checked robustness to a bunch of parameters and the effect of tides and stuff. And I'm not going to talk much about that part, but you're welcome to ask about it if you like. So let me show you a few examples before we get into the full results. So this is an example where the resonances were all maintained. So you can see here that this looks a lot like the plot I showed you before. All of these same resonant angles are still confined to a given region. So they're all still librating. The resonance was not affected when there was, 2% of an Earth mass in rogue planetesimals. Now let's crank it up a little bit more. When it was about 4%, well, you can see here things are a little different. For the top angle is still bouncing around 180 degrees, but the libration amplitude is a bit wider. Right? So it's a little bit further from kind of the most beautiful deepness in resonance, but it's still resonant. Some of these angles are kind of barely resonant, but this still counts as resonant in my book. But just a little bit stronger perturbation, and boom, the resonances go away. So you can see in this case with 6.5% of an Earth mass in rogue stuff, then you can see the resonances are there at the beginning, but then they get washed out. Because the planets are removed from resonance, they're no longer lining up as they used to. And so why does this happen? In detail, the reason this happens is because the planets' orbits separate. They get slightly further apart. And this plot is just showing a very simple example of this, focusing on the outer 3 planets. So what you're seeing is the relative drift of the outer 3 planets in this top plot. And you can see the amount that they're drifting apart is pretty small. Here it's on the order of 1,000th of an AU. That's not a lot. But it turns out that the width of these resonances is really small. And so the resonances that characterize those outer planets are, measured in units of kind of 10 to the minus 4 AU. And so by moving by 1,000th of an AU apart is moving apart by more than the width of the resonance. And so the planets can leave the resonance. And so you can see there's kind of a time frame around here, around after a few thousand years in this example, where the planet's orbits have separated enough that all these resonant angles kind of stop librating and start circulating. So the resonances are broken. And you can do some simple math and figure out exactly, about how much mass we think it should take to do that. And it depends on a few parameters that I'm not showing you. But kind of the gist is that when the planets are spread out by more than the width of these resonances, then they leave the resonance, of course, and that's something that we can constrain. So if we look at this for a whole population of different simulations, here you see 1,000 simulations of basically of the Trappist-1 system plus a single rogue planet. And I've labeled them with different colors. So the blue ones are ones that are consistent with the present day system, where all these angles still vibrate. They're still in resonance, in a resonant chain like we see. The red ones are simulations where the planets survived for the full 10 million years of the simulation. And the black ones are ones where the planets did not survive, meaning that they, the planets in the actual Trappist-1 planets bashed into each other. Right? So in all of these cases, the rogue planet went away, usually by colliding with a planet. But in the blue ones, the system as a whole survived and stayed resonant. In the red ones, the system as a whole survived but was not resonant. And in black, the system as a whole did not survive. And you can see the x-axis here is how massive that rogue planet is. And so like you might expect, a more massive rogue planet gives a big, stronger perturbations. And so it takes less time to destabilize the system. And a lot of these red ones on here actually will go unstable on longer timescales. So they probably are not protected from that. But the blue ones should stay nice and stable for forever. And we tested it out to 1 billion years and it stays stable. And so what's the punchline here? Well, we see a system that's in resonance, in in this resonant chain. And so the maximal perturbation that still retains the resonances is kind of this blue dot here. And that blue dot there is a little bit more than 1/100th of an Earth mass. It's about a lunar mass. And so what does that mean? That's the absolute maximum late mass of a single late impactor that could have happened. So if there was only one leftover rogue planet in the system, then it couldn't have been more massive than about the moon without disrupting the system that we see today. And if there was such a case, then you can see the impacts are most likely on the outer planets. And that's kind of interesting. Right? So if we look at the kind of probably more reasonable case of a swarm of leftover planetesimals, the idea is the same, right? So again, the blue things are consistent with the present day system. The red and black ones are not. The black ones are totally unstable. The red ones may go unstable in the future, but they're not yet. And you can see this pretty clear division between, resonant and non-resonant that happens at about 5% of an Earth mass. So the maximum total mass in leftover rogue planetesimals is about 5% of an Earth mass. And now we'd like to translate that into impact fluxes. And so what we can do is basically look at, in all the simulations that did retain resonant chains, which planets were getting impacted at what rate, and then assume that we had the maximum possible total amount of rogue stuff and see how much stuff could have bashed into each planet. And that's really kind of a simple experiment. And so you can see for each of the 7 planets I've just listed their orbital distance, and then the maximum bombardment mass in Earth masses. And so you can see those numbers, they don't necessarily mean a ton immediately. And so in simple terms, the inner 4 planets cannot have been hit by more than what hit the Earth, right? So remember, on Earth, it was about 0.5% of an Earth mass. So 0.005 Earth masses of stuff. So all those 4 inner planets cannot have been hit by that much. The outer planets can have been hit by about as much as on Earth, or maybe slightly more. They're kind of consistent with the upper limits on Earth's late accretion. And so this kind of shows the power of this very simple technique, looking at the resonances, because even though the system is 40 light years away or whatnot, we can put upper limits that are about as stringent as we can for the Earth using a different technique. And the fact that there's very little late accretion tells us the planets had to have formed fast. There was not much action after they formed. So let me do a little tangent into the formation of those kind of systems. So we'll go a little bit into formation models for super Earths. So in general, super Earths are one of the most abundant populations of planets that we know of. They exist around something like 1/3 of all stars. And they often come in systems with multiple planets. And one key constraint on how they form is their period ratio distribution. excuse me. So what that is basically anytime there's more than one planet in a given system, look at the ratio of their orbital periods and throw those in a bucket. And then you have a bunch of, period ratios. And this is the distribution. This is the cumulative distribution in this plot of the period ratio distribution of for all planets less than about 4 Earth radii in the Kepler sample. And so the way I usually introduce is that, this kind of curve doesn't really say much to most people. But what's more interesting is what it doesn't look like. It doesn't look like a staircase, right? A staircase would happen if planets really like to be at specific period ratios, meaning in certain resonances. And so if you looked carefully before, you could see tiny little blips in a couple spots, but you don't see an obvious staircase like this one. If half of all planet pairs were in 3:2 and half were in 2:1 resonance, you'd see this staircase, and you don't, right? So in terms of formation models, that's an important constraint. Nonetheless, I will argue that all roads for the formation of these systems lead to migration. And so why do I say that? And so the simple reason is simply that migration timescales are so short. And so what this plot shows is basically a very simple estimate for the migration timescale for a bunch of different Kepler planets. And so assuming that they formed in a disk with certain characteristics that are pretty reasonable, how fast they should migrate according to our current thinking. And the punchline is they should migrate really fast. So you can't just ignore migration. It must have happened. The details are still being worked out, but migration must be an important part of the story. And so what is this migration thing of which I speak? Well, it's basically a gravitational interaction between growing planets and their gaseous disks. And this simulation shows this is a snapshot from a hydrodynamical simulation where there's 5 different planets in the same disk. Each of those planets is about 3 Earth masses. And you can see they're each spinning out these cool kind of spiral density waves. And if you squint and look very carefully along the orbit of each of these, there's also perturbations along the orbit in the co-orbital region that cause other torques that cause migration. Okay? And so migration is important for planets when they're more massive than Mars or so. And more massive planets migrate faster, right? Those are kind of key things to know. A kind of final thing to know in this context is that migration probably doesn't just dump planets onto the star. We think that disks generally have inner edges, and there's a counterbalance torque at the inner edge of disks that stops migration. And so planets won't just fall on the star, they'll tend to migrate inward and get trapped at the inner edge. So putting this together, assuming that a population of planetary embryos is formed within a disk, what we think should happen, and what happens generically in simulations, is that these things start to migrate. They migrate inward. They don't just all collapse into one planet. They tend to form resonant chains of planets, like the ones that we see, where the innermost planets are kind of anchored at the inner edge of the disk. And so the typical resonances that we see are things like 4:3, 3:2, 2:1, those kind of resonances. Now, of course, this is the kind of thing that we see in Trappist-1, but not among most super Earths. So why is that? Well, when the gas disk goes away, most of the time, these systems probably don't survive. They have late instabilities that lead to collisions between the planets, and those tend to spread out the planets and destroy the resonances. So if we look again at this kind of period ratio distribution that's not that interesting, now the red curve now is this staircase. Those are the resonant chains that form in our simulations, kind of while the gas is still there. And the blue ones are after the systems go unstable. And the punchline is if you mix those two together, can match the distribution. And for that to work, the vast majority, maybe 98% or something like that, of resonant chains must go unstable. Even though they might form a lot, they probably are mostly destroyed pretty easily. So the question you might be asking yourself is, well, then why is Trappist-1 the one that survived? Okay? And I would say that I think that possibly the simplest explanation is that just because its gaseous disk was pretty low mass, which kind of makes sense. It's a very low mass star in itself. So why do I say that? Because in the same kind of population of simulations of the formation of resonant chains that then get broken, we can look at which ones survive and which ones don't. And so what this plot is showing is the period ratio distribution of stable and unstable resonant chains. Okay? And so the brown ones are unstable and the red ones are stable. Sorry, it's not the easiest to decipher plot, but the brown ones, basically the ones on the left, further to the left are unstable, went unstable later. The ones on the right stayed stable. And so what's the difference between those? That shift left and right is such that more compact systems are more likely to go unstable, and also systems with more planets are more likely to go unstable. And in simulations, that's often 10 or more planets in a resonant chain. And so kind of putting these logical pieces together, the migration speed is, roughly linearly proportional to the disk mass and the planet mass. Lower mass disks probably make smaller planets that also migrate slower, and those tend to form, there's less squeezing basically for slower migration, and so they tend to form less compact, more stable resonant chains. So that's the argument that I was making, why I think a low mass disk can explain why Trappist-1, the resonant chain survived. All right, so kind of back to our original story. Let's look at the growth of the planets and in the context of late accretion. So now what we're seeing is basically the growth curves, the fraction of final mass as a function of time for different objects. In blue are planets taken from one of those simulations that include both pebble accretion and migration, and the staircases here are from impacts between embryos. So they can easily grow, bash into each other, but since this is all happening very early while the gas is still around, just reform a new resonant chain. And so in this system, it formed a pretty good Trappist-1 analog, which is why we mined that one from the simulations. And then these other curves in black are cosmochemically constrained, very rough, of course, growth curves for different solar system objects. So Vesta is constrained to have been fully formed within just 1 million years or so. Mars within just a few million years, and Earth's growth took longer. And there's different kind of estimates on that. And the moon forming impact itself had to happen quite a bit later. And so what's kind of cool is in terms of the late accretion constraints we have, the ones from the Earth, time 0 is the moon forming impact. The ones from Trappist-1 are when the gas is going away, so much earlier. So in some sense, they're more constraining because time 0 was earlier. And so let me move on to the last part about water. And so now we can say, well, if we have constraints on the late accretion onto these planets, if we assume that they may have, those late impactors may have had some water, we can put upper limits on how much water delivery could have happened by those impacts. And so that's what's shown in the last column of this plot now. Last column of this table, I guess. And so the unit of oceans, one ocean is the amount of water on Earth's surface. And so you can see that if we assume a significant water content for the impactors, the outer planets could have gotten a few oceans of water, but the innermost ones, not very much at all. And we'd like to compare that with how much water is on the planets themselves. So how much water do they have themselves anyway? Well, this kind of, mass radius curves like we were showing before can give very rough estimates, and more detailed models of the interior structure can do better. And so we can try to do that. The trick is that there's a degeneracy between basically the mass in the solid part of the planet, the density of the solid part of the planet, and the amount of water that can fit to still match the mass and radius constraints. And so this is illustrated nicely here. If the planets each had a 50% iron mass fraction, then they would need a lot of water to compensate to match basically the sizes of the measured sizes of the planets. In contrast, if they have very relatively low density, low iron content cores, then you need a lot less water to match the constraints. And so we ran a new sets of models that varied both the solid part of the planet structure, or making different assumptions, and then modeling an outer water layer to see what could fit the data. So done by Caroline Dorn right here. So let me summarize what we found. So what we're seeing here is a series of plots with the water content versus orbital separation. And that dashed line is basically one Earth ocean, Earth surface water. So these 5 models are presented here for each planet. And so what you can see is each of those shows kind of the solid error bars or whatnot show 1 sigma and then 2 sigma values for the models. And so you can see immediately 2 things. The inner planets look pretty dry. They're consistent with having very little water. And the outer 4 planets are all consistent with having a few % water by mass. But unfortunately, the 2 sigma error bars for each planet go down to 0. And so we can't really be that confident that any of the planets must absolutely have a lot of water, even though it seems circumstantially like they probably do. Now, here are the constraints from late accretion. So these are upper limits on how much water could have been delivered by late accretion if those objects were pretty water rich. And so what you can see is for the inner 3 planets, those are above our estimates for how much water they have. So in theory, if there's a little bit of water there, it could have come late from late accretion. In contrast, for the outer planets, if their water contents really are pretty high, of a few percent by mass, then we cannot explain that from late accretion. If there's water there, it must have been incorporated earlier while the planets were actually forming. And a final kind of interesting thing here is that the temperatures on these planets probably evolved quite a bit early on in their formation, because basically the central star, which is a very low mass star, it takes about 1 billion years to reach the main sequence. And so the temperature basically was hotter early on, brighter earlier on, as it was contracting. And so this vertical gray line here shows the inner edge of the habitable zone, beyond which you have to be to the right of this curve of that line for liquid water to survive on a planet's surface. And you can see that kind of march inward in time. And so there's probably a long interval during which many of these planets could have lost water, even if they had it. So let me just do a quick comparison between Earth and Trappist-1, kind of using late accretion as a guide. So formation timescale, it was probably something like 100 million years for Earth in terms of the moon forming impact, whereas for Trappist-1, it must have happened much faster. The amount of late accreted mass on Earth, something like 0.5% of an Earth mass, whereas on Trappist-1, it was roughly that amount for the outer planets and quite a bit less for the inner ones. Of course, the technique was different. For the Earth, we can use highly-siderophile elements. For Trappist-1, we can use the survival of the resonance, this clean baby thing I was talking about. The time zero for late accretion is different. It's the moon forming impact for Earth. It's the gas disk dispersal for Trappist-1. And finally, a thing that they have in common is in both cases, late accretion seems like it cannot explain how much water they might have. And so any primary water delivery had to happen before late accretion. So finally, let me just wrap up with a couple philosophical points. One is to say that resonant chain systems are really valuable. First of all, they tend to have lots of systems with low mutual inclinations. So you can often find multiple planets in transit in the same system, which is pretty cool. They also provide very strong transit timing variation signals, which helps in measuring masses. So what this plot is showing is basically the rough amplitude of transit timing variations as a function of period ratio between planets. And those peaks are at resonances. And so resonant chains have very strong amplitudes, so you can hope to constrain their masses much more effectively than if they were not in resonance. And this, of course, feeds into measuring bulk densities and constraints on composition. And finally, of course, resonant dynamics can give you some constraints on late accretion and formation. There's kind of an interesting little side note is that the definition of a planet states that a planet has to orbit the sun, be massive enough to be roughly round, and have cleared the neighborhood around its orbit of leftover junk. And so for Trappist-1, if you accept that it's obviously not the sun, but if we accept that it's a true star, and there are studies showing that the planets probably had to be round to match the transit light curves, and we've shown that they've cleared their neighborhood. So we should definitely call them planets, I think. So let me just summarize now. The resonant chain of Trappist-1, you can consider it kind of a clean baby, like I was saying, that has not been throwing stuff all over the place. And so we can't say exactly how much stuff hit the planets, but we can put upper limits on what could have been, the impacts. There can't have been late impacts more massive than a moon mass. And in that case, there would have just been one rogue planet that collided with one of the planets. Late accretion on each planet is less than or comparable to on Earth, which is pretty good precision, from this resonant dynamics perspective. It implies that the planet's formed fast. So if there is any water, it must have been incorporated during the planet's formation. And in principle, this should be generalizable to any resonant chain system out there. All right, I'll stop there. Thank you.
Thank you so much, Sean. This was a very amazing talk. Yeah, I enjoyed it a lot. Now there is time for questions. And for those of you who want to raise a question, you can write your question in the chats or simply raise your hands. And while people are coming up with questions, I have a question about, so you said the majority of water must have been accreted during formation, and I wonder if there are additional constraints that we can put on when interpreting planetary interiors. For example, maybe we expect the water budget to increase with planets at larger orbital distances, but is there something in addition to this, or to have it more quantitative, given your models, or knowing that most of the water must come from the time during formation?
It's tricky because there are a lot of different factors that go towards planets farther out having more water. Like you say, they could just be closer to the snow line, where there was a source of solids to build the planets. They could also be that impacts are a little bit less energetic further out, so that you lose less water. There's also, in the case of Trappist-1, or a planet around a star, planets around a star that contracts very slowly, like an ultra-cool dwarf. Planets further out have a much shorter interval during which it's too hot for water as well. And so it's tricky to disentangle these different factors. And so each of them goes in the same direction. So saying which one is the dominant one is tricky.
Okay, yes, thank you. There is a question by Judith. Judith, please go ahead.
Hey, Judith.
Hi. Hey, how are you? That was a really nice talk. Thank you very much. So do you think that we should now not teach at all the late veneer hypothesis on our classes on planet formation, or do you think it still has any validity?
You mean the idea that the water came during the late veneer?
Yeah, exactly.
Yeah, I think that's pretty much ruled out. Yeah.
Okay.
So that idea has been ruled out for a while. Oh.
Okay, cool. And do you think that in planet formation way, the Earth is quite dry, actually, right? It has relatively small amount of water in comparison to the planets in the outer solar system. So do you think that means that Earth really formed, say, in the inner solar system and created at one point a bit of icy material, or do you think that it could have formed beyond the snow line, migrated inward, and lost the water?
I think signs go towards Earth, never having a ton of water and not losing a ton, just because, like, for example, its isotopes are pretty close to those of non-carbonaceous meteorites. So it's harder to imagine that if it started way up past the snow line, then came inward and lost a ton of water. So I would guess that it's more in the case of it never having a ton. From a dynamical perspective, it's kind of hard to explain how to avoid that, because there's all these processes that mix stuff up so efficiently that keeping all the water-rich stuff away from the Earth is the challenge. Back in the day, when I started this kind of business, it was like, well, how can we figure out how water got to Earth? And now it's reversed, and we're trying to figure out, well, dynamically, how do you keep that water-rich stuff away from Earth?
Okay, cool. Thanks a lot.
Thanks.
There is a question by Joachim. I will just read it out loud.
Hey,
can you constrain the libration amplitude for exoplanets using simulations or TTV data? And the second question, what refinement to the constraint could this give?
That is a good call. And so we're trying to do that kind of thing right now. So that's the trick, is that you need a lot of data to really put strong numbers on the libration amplitudes, because there's just not a long enough time baseline, and there's not enough constraints, because you get data basically every transit. You'd love to have thousands and thousands of transits, but then you got to wait forever. And so there's combinations of trying to match the transit timings and all the other parameters at the same time. Those give you a certain range of best fits. And from the current sample done by people like Simone Grimm and Eric Agol, they get a pretty consistent picture that, libration amplitudes are within a given range, but they can't be as precise as you'd like. If you could get really precise ones, that would be really nice. Because the story that I was telling, I keep waiting for people to point out there's a slight logical inconsistency in my whole experiment, which is that ideally you would want the Trappist-1 system that you start with to be representative of right after the gas went away. So you want, like you're saying, libration amplitudes probably to be even smaller than they are now. But rewinding the clock in that direction is surprisingly hard. And so I did a few little experiments trying to damp out the libration amplitudes, and it's not that easy to do. And so the experiment still kind of shows the principle, and the idea works pretty well. But in theory, you would want to be able to rewind the clock slightly further.
Thanks, John. Great talk.
All right, thanks very much. It was good to see you.
Very good. Are there other questions? Otherwise, I also have a question. You mentioned there are also other resonant chain systems, right? Mm-hmm. And are they all probably were they all formed in low mass gas disks, or are there some that are exceptions to this?
That's a really good question, and I don't know the answer. So that low mass disk argument for why resonant chains would be slightly less compact and so a little bit more stable, it kind of makes sense, because if there's a distribution of disk masses, and usually that they do a certain path, and once in a while they do this other path, and the reason for taking that other path is the ones that have low mass disks, then that can make sense. It doesn't always work, because there's cases such as GJ876, there's some gas giants involved. HR8799, there's some mega Jupiters involved in a resonant chain. That one might be a slightly different category, but still the same idea. So I'm not sure we quite understand exactly what the branching point is for which ones remain stable and which ones don't. So I think low mass disks kind of go in the right direction, but it might not be the full story.
Cool, thanks a lot. So we still have, only 1 minute, like in theory, but so now it's the time to ask your final question. I really don't see any other questions. Well, in that case, I will thank you again very much. It was a great pleasure to have you here. It was a very nice talk. I enjoyed it very much to see for the first time the talk on this topic. Yes, and I hope to see you soon. Then in April in Zurich. That would be very great. Yes, thanks so much.
Cool. Well, thanks very much. I appreciate it. It was fun.